All right, we've been looking at the second fundamental theorem of calculus, which indicates that we're performing two operations back to back that are inverses, and we discovered a shortcut. So let's take that shortcut and put it into practice with these examples here. All right, for this first example, we've identified a differentiation and an integration. We see we have a variable limit. Okay, so in that case, using the second FTC, okay, the first thing I'm going to do is find the derivative of the variable limit, which is 1. Then I'm going to multiply that by the replacement of the integrand's variable with the variable in the limit. So cosine x. And that's it. If I wanted to go back and perform integration and then differentiation, I should end up with cosine x. But why? We want to avoid all that work. All right, come down here. Differentiation, integration, studying the variable limit here for our x. Okay, first step, find the derivative of x is 1. And then everywhere I see a t, I'm going to replace it with x. So it appears that my answer is just going to be the square root of x squared plus 1. And it would be. And let me say this about the second fundamental theorem of calculus. It's very convenient when, if I wanted to go through and find the antiderivative, I couldn't, okay? And I wanted to find the derivative, I have a shortcut to help me. So it's nice because in this particular problem, I couldn't find an antiderivative and take the long trip, the long road, if you will, okay, improving the shortcut. Couldn't do it here. So it's nice to know that I can undo something that I'm doing through this shortcut. All right, differentiation. Okay, pay attention to these limits. We haven't seen this case yet. Okay, what we want to do is typically we want to have the variable limit as our upper limit. So what I'm going to do is I'm going to rearrange. It's been a while. There's a property that's going to allow us to switch these limits. And you might well remember that if I do trade limits like this, that the effect on the integral is to take and find its opposite. So I'm going to have a negative here. So it would be okay to pull the negative completely out front here. So by switching the limits, I make the answer negative or find its opposite. Okay. All right. Differentiating an integral shortcut. My answer is going to be, let me come down here. Yikes, running out of room. The opposite of, the negative of, find the derivative of 5x squared, 10x. Okay, and then multiply by sine of 5x squared. Replacing 5x squared in here. So first find its derivative and then replace it in for every variable in your integrand. That should be it. All right, right here. Okay, the limits look like they're in good shape. I want the constant to be down here. There's a lower limit. All right, let's find the derivative of x squared plus 9, which is 2x, times, I'm going to have sine, okay, of t gets replaced with x squared plus 9. I am not going to cube this quantity right here. I'm going to leave it the way it is. And those should all be correct. Using the idea of the second fundamental theorem of calculus to get our answer really means we're using a shortcut, a two-step shortcut. Okay, I want to show you some change in some notation here with these examples. Okay, notice how these compare to the last ones. All right, we're told that this function is defined by this integral here, as are the other three. So f of x is equal to these integrals with the variable limit. But the objective here is to find f prime of x. Okay, so I'm actually just going to differentiate both sides of this equation. This is kind of in an equation, well, it is in an equation format as opposed to the previous example that was just given you if you were given the problem. All right, so what I'm going to do is if I'm asked to find f prime of x, I know to get f prime of x, that means I'm bringing in a derivative operator. And what I do to one side of the equation, I've got to do to the other. So working down, right here, that notation is f prime of x. So what does that mean? That means that I have exactly what I just got done doing. The situation where I can use the shortcut method. So making sure everything's in good shape. Yeah, variable limit. Let's find the derivative of sine x. Now, we haven't seen that yet. I think we've been mostly working with power functions. So the derivative of sine x is cosine x. Derivative of the variable limit times, now let's look in here. Everywhere you see t, replace it with sine x. Cosine of x times e raised to, I've kind of covered that up. I think it was t squared. So sine x here. You could do a little cleanup, I guess, but I mean, this is fine here too. And what I mean by cleanup is this. Cosine of x times the e function raised to the sine squared x power. All I mean is you could put the square on the trig function. All right, so sometimes students get kind of spooked up by the notation, but I mean, think about it. This is a function defined by an integral. They want you to find the derivative. So differentiating both sides just means that you're back to the second fundamental theorem, the shortcut. So bring in d over dx to both sides of the equation. Oh, you might have first noticed that you'd want to switch these limits here. Okay, so before I even brought in the d over dx, that might have been a good thing to do, but I'll go ahead and incorporate it right here. So f prime of x is equal to, let me switch the limits, and so I'm going to have the opposite, okay, here. Try not to do too much in one step, I might lose something. All right. So the opposite, these two are going to cancel, if you will. Find the two things, derivative of x, which is 1, and then replace x in for every variable. Negative 3x sine of x. Two more examples. Same objective, derivative operator, correct notation. Two inverse operations, limits look like they're in good shape. Okay, they're going to undo each other. Derivative of the limit times the integrand's variable replaced with the variable limit. So that would be times 4 quantity sine x. Perhaps a little cleanup here. I'll probably just put the 4 in front, and I have the cosine x, and you could pull the 3 on the trig on sine here and have sine cubed x. One final example, bring in the d over dx. F prime of x equals, these two are going to cancel. Variables in the locations I want them to be in. Derivative of x is 1 times 1 over 1 plus x squared. So just some practice with the second fundamental theorem of calculus, which really means the shortcut.